Okay, probably we will start our QFT stream seminar. And today it's a pleasure to have Pujian Mao from Tianjin University, who will tell us on the 5D while double copy.
Okay.
So please.
Thank you. Yeah. Let me start by thanking for the invitation. Thanks, Hossein and also Luis. It's my first time to be here. I so many great people, and it's a really great place. So my criteria for great place is I can see blackboard anywhere, big blackboards. So for sure, here's the top place. So I'm very happy to talk here. So I think you are happy to about my comments, right? This is also your request. Today I will try to convince you there are some nice connections between gravity and gauge theory at the classical level. So in particular, our contribution is to extend those connections I mentioned to higher dimensions. We present the first example in 5D, and we are working on 6D, and we believe our framework can be generalized to any dimensions. Of course, you can do one by one because I cannot leave an arbitrary number for the dimensions, but for any dimensions, I think. Because 5 is the odd dimension, 6 is the even dimensions. So once you have results for both, and I think you can really extend to any dimensions. Well, the materials are based on those two papers, work in collaborations with Junbao Wu, professor, another professor from Tianjin University, and PhD students under our drawing supervision. So I will start from the double copy relations. It's an amplitude relation. Well, somehow this is the motivation because people realize that first, and then the question is, can we realize the double copy relation at the classical level? This is very recent observation. I think starts like 10 years ago. And then there are two realization of classical double copy. One is based on the curve sheet form. Another is a Weyl double copy, which is I'm talking. So also I will give a short review in the 4D case, how much people already know. And then it's our new contributions about 5D Weyl double copy. Okay. Well, I guess some people knows that the first example should be the KLT relations back to 40 years about open string connection between open string amplitude and closed string amplitude. While here, I will present the BCG duality because it's I think it's more somehow formal, and you can present the concrete relations or what is hidden between those connections is from the color kinematics duality. So a very simple example is let's look at the 4-point tree level N Weyl's amplitude. You have this well-known UST channels. It's just a sum of those three terms from the three diagrams, and C and or N are the either color factor or the kinematics factors I will show later. And UST are the standard kinematics invariance of momenta. Okay. Now, once I give you the present concrete formulas of the C and the N for each channel, you will recover those two relations. So while this one you can find from the group structure, this is the kinematics relations. You find the color, somehow the color information and the kinematic information satisfy the same relations. And then the idea is, can we exchange them? So here you see in this amplitude, there's C and N for all the three channels. So now the question is, can we replace all the C by N? Once you do that, you find the result is also an amplitude. There are some nice properties. So the external states are captured by symmetric polarization tensors. So somehow like a spin 2 particle. And the integrations are of two derivative types. And then it's invariant and linearized diffeomorphism transformation. So while I don't know if it is the only theory that we know satisfy both all of those properties, but for sure, Einstein's gravity satisfies all of them. So in the end, you have an amplitude for gravity. So this is a connection between gauge theory and gravity at the amplitude level. Then the question is, can we find something at the classical level? Namely, we are looking at solutions directly. Classical solutions just satisfy the equation of motion. Probably, I think for sure there are some hints or indications before, but only when, like 10 years ago, by this group of people, they find this observation that if you use the curve-sheet form, suppose your metric can have this decomposition. So the form metric can be a summation of flight metric eta plus phi times k two null vectors, like a product of two vectors. So somehow this is the hint of double copy, right? Two gauge fields, the summation of the product of two gauge fields will be like a graviton fields, right? And the next step is, can we say something from the equation of motion, classical equation of motion? Once you do this curve-sheet somehow decomposition, and also there are some nice properties from this decomposition, because once this vector k is null, you can prove that first this is a null vector with respect to the form metric J mu nu. But if your metric can satisfy this curve-sheet form, you can prove that this k is also null with respect to the Minkowski metric eta mu nu. So you can raise the index of k by either g or eta is the same thing. And then the next steps, this group of people somehow insert those decomposition to the Einstein equation. So you can check what you can have for the rich tensor. They have some conditions. First, the zeroth direction they set to be 1, and also they assume that this is stationary case, namely everything is independent of t. Once you assume that, you find that Ricci tensor can be right in this way. And you can somehow already recognize something. This is like a wave function for scalar fields. If you define phi k mu, the product of phi k mu as a vector a mu, and you see this equation is the source-free Maxwell equation. Literally the source-free Maxwell equation. So now in this somehow simpler setup, suppose your metric admit the curve-sheet form. That's the first assumption. The second one is you assume it's a stationary case. So everything is independent of time t. In this case, you can cite the zeroth component of k to be just 1. Then the full somehow gravitational fields, the J mu nu, can be written as a product of gauge fields plus scalar fields. Well, probably you just cannot recover those nice observations or structures. I mean, the point is, here of course, it's not the full theory are equal to the full theory of Einstein gravity equal to like a Maxwell theory. If that's the case, people would know that before, right? This is, we are trying to find which part of this gravity theory can be written as a product of gauge theory. So they present the first example. Of course, afterwards, there are more works, and also we are trying to generalize to higher dimensions. So the point, of course, we can believe it cannot happen that the full Einstein theory just a product of Maxwell theory, right? So now here's just how you can reduce to that case. So this is the first example of classical double copy relations, namely a solution of gravity can be written as a product of solution of gauge theory. Here's abelian gauge theory, Maxwell theory. Okay, well, this is related to your question. Maybe you can ask, how about gravitational waves like PP waves? Well, for this kind of solution, people do not have somehow a generic structure, but you can check case by case. Suppose you give me a PP wave solution, and the curve sheet form are just like this. So, you can have the full metric from those ingredients by the curve sheet form. And the Einstein equation, for those ansatz, is equivalent to the wave equation. Like somehow here the gauge field is trivial. It's only like 1, 0, 0, 0. But the non-trivial things, the scalar fields, is satisfying the wave equation. Somehow it's scalar particle propagating in the space-time. This is equivalent to the PP wave solutions. There are for sure a lot of examples which I think I don't want to mention case by case because you can check there are like hundreds of papers in recent years within the 10 years because this paper the citation is more than 300. Most of them are looking for those type of decomposition case by case. Yeah. Okay, so while if we believe there are some kind of intrinsic connections between gravity and gauge theories, we can ask which guy should be the right quantity to look, because the point here is we can use vector, we can use curve sheet form, but the point is the curve sheet form is very sensitive to the coordinate system you choose. It's valid in one coordinates, but it's not in another coordinates. So that somehow this means we are not looking at the right guys for series. Like we should look at the propagating degree of freedom, not the gauge degree of freedom, right? Like the metric and the gauge fields, we know that they are not the physical observer. Any questions? Okay. And then the next version of classical double copy is the Weyl double copy. So people start to look at directly the physical quantities, the Weyl tensor and the Maxwell tensor. Of course, here I should introduce some notations. Normally people do starts from the Pauli matrix. You can construct the Van Waden metric, and then you construct this guy, which can convert quantities between or from the tensorial language to the spinor language. And then you can write the Weyl tensor in the spinor language, and you find the right decomposition or the right connection between gravity and gauge theory should be this one, this Weyl double copy formulas. The Weyl tensor equal to the product of Maxwell tensor plus this scalar fields. Well, of course, you can ask, this is algebraic relations. You can write whatever gravity theory as the product of these things. So what should or why this is interesting? Because you need to check, all the information is encoded in these scalar fields, which kind of equations the scalar fields satisfy. And the other questions, if you can find, or for each solution of gravity theory, if you can find the decomposition like this. This is the question we can answer from the Weyl double copy relation. First, for the algebraic spatial solutions, the type D case. You can have the Polanyi-Damianski metric. Well, it's believed that this is the most general type D solutions. The metric can be written in this way. There are two functions P and Q. While in those two equations, all the quantities except the coordinates are constants. So you have like 7 free parameters in this line element. And then we can convert the information from Polanyi-Damianski to the spinor language. I can write the Weyl spinor in this way. And I know there's a solution of Maxwell theory can give you the field strength spinor in this way. Then I can find the scalar fields. This is algebraic relations. And then you can check that this scalar fields satisfy the wave equation in the flat background. That's a very important thing. So that means, well, if you believe Polanyi-Damianski is the most general type D solutions, that means for every type D solutions, you can find a Maxwell fields plus a scalar fields, which satisfy the wave equation, can satisfy the decomposition like this. So that means for every type D solutions, Weyl double copy relations. So you have a somehow identical Maxwell fields. So FAB and FCD, sorry, this is a typo, this should be a capital C, are the same Maxwell fields. S is a scalar fields, satisfy the wave equation. Yeah. And also you can check for another case, the type N solutions. For this case, we can verify the Weyl double copy relations from the equation of motion level. So now I directly write the relations in the NP language, Newman-Penrose formalism. I suppose you guys at least know this. Newman-Penrose language is a theta system with for now basis vector. And you write 10 independent Weyl tensor, 10 independent components of Weyl tensor by 5 scalar fields. Because the spacetime is very special, algebraically special, it's type N. You have a repeated now principal directions and etc. With those conditions, the only Weyl scalar is this psi4. And the Weyl double copy relations is just psi4 equal to phi2 from the Maxwell theory, a degenerate Maxwell theory, phi2 square over S. Then the equations of motion for them are that the Bianchi identity for the Weyl tensor, the Maxwell equation for the Maxwell fields for the phi. Now suppose you have a gravity theory, a solution of gravity theory. That means you are psi satisfy the Bianchi identity. Suppose you accept this decomposition, and also phi is a solution of Maxwell theory, and you can plug in this decomposition to the Bianchi identity, which can give you the equation of motion for the scalar fields S, right? Somehow you just plug in the right-hand side of this part to the Bianchi identity equation, the Bianchi identity, and then simplify this Bianchi identity by the Maxwell equation, by those two equations. You'll be end up with the scalar fields equation. The nice thing is those two equations are integrable. Namely, you can always have solutions for those two equations. That means for every type N gravity theory, for any type N solution of gravity theory, you can find a scalar fields plus a Maxwell fields can have this decomposition, the Weyl double copy decomposition. Moreover, the nice things with those two equations, you can verify that this S must satisfy this wave equation on the curved type N background. Procedure, how you can see this relation, or why this is interesting. Because this is a proof from the equation of motion level that for any Tappan solution, for any Tappan gravity solution, you must have this decomposition. S satisfies the wave equation on the Tappan background. Phi satisfies the Maxwell equation also on the curved Tappan background. Yeah. So this is done by Bob and his collaborators. Here the Goldska square, because some of you know these twins. So there are two Goldska. Unfortunately, both of them quit. So when I try to talk to them, only those two senior guys are left. Those three young guys are left. So they cannot answer any question. Yeah, indeed. Better job, much better. Okay, now I have two remarks. The first thing is the decomposition of the Weyl spinner and somehow the connection between the Weyl spinner and Maxwell spinner. Because in this two-spinner language, you can always somehow split the Weyl spinner into this form by 4 independent spinner, and you just symmetrize the index. You can do the same thing for the Maxwell spin. And then suppose this is a square of this guy. This spacetime must be either type D or type N, because you will have a AB, or here if it's algebraically general, you will have AB, right? That's type D spacetime. If this is algebraically special, namely you have A, here you will have 4A, that's type N. So if you want your Weyl double copy relation based on the identical Maxwell fields, namely the same FAB, then the gravity solution of the spacetime must be either type D or type N. And then those two cases prove that all of them satisfy. For type D, you have Plaminsky-Damiansky. Almost, I mean, there's no uniqueness theorem claiming that PD solution is the only or the most general, but I mean, this is the most general solution we know. Okay. For type N, we prove that from the equation of motion level. That's already all the case we can have, right? Of course, you can somehow generalize or relax the condition. You can use two different Maxwell fields to construct the Weyl tensor. Then this is another story. This should be more complicated. Of course, people are working on that, and we hope there can be some nice observations soon. That's point one. The other remarks is that in the, if you don't ask any algebraically spatial condition, just in the NP formalism, the 4 Weyl double copy relation should be written in this way. Now you have all the 5 complex Weyl spinner plus the most general Maxwell spinner, and that should be the connections between them. Okay. Then it starts our job. We were asking ourselves, can we generalize the Weyl double copy relation to higher dimensions? Well, there are several motivations. First, from amplitude side, the BCG duality or the BCG relation, I think it is valid in any dimensions. There's no space-time dependence. That's point one. Another version, classical Weyl double copy, where we are based on the curve-shade form. Of course, you can have this curve-shade form in any dimension, in arbitrary dimensions. There are some examples about the curve-shade double copy relations in 5D or in other dimensions. But there's no any works before us about higher dimensional Weyl double copy relation because this observation is based on the Spinner language. Well, if you are familiar with Spinner, somehow you believe 4 is the very special dimensions. you have very nice properties. You can have the twistor series, etc. So how about higher dimension? In particular, odd dimensions. That's our motivations. Well, to present our construction, we need to know some basis. So in 5D, you do not have like an NP formalism. You cannot choose all your basis vector now. Normally, people choose this, well, just a standard Weyl-band formalism. You choose 2 null vector plus 3 space-like vector as your basis. And then you can, or we introduce some directional derivative in this way. It's D associated to L, capital delta associated to N, and then the small delta I associated to Mi. Here you have 3 space-like vectors. Also, basically, there's some notations about work in the following pages. So the spin coefficients associated to L, N, and M are the capital guys, capital L, capital N, capital M. Okay. Now, previously, we know that in 4D, if you start with identical Maxwell theory, you can only construct the Weyl double copy relation for either type D or type N. Now, of course, in higher dimensions, we start from the simpler case. Of course, we want to know the algebraic classification, but this is very different in higher dimensions. It's no longer, I mean, as transparent as the principal null direction, etc. But luckily, this there are the CMPP classification, basically based on the boost order of the basis vector, either L or N. So somehow, suppose you can associate a boost order -1 to L, +1 to N, and then for all the M are 0. And then you can define the boost weights for the decomposition of 4 Weyl tensor. For type N solution, you only have either this piece or this piece. So this classification is only based on the boost weights. So that's our starting point. We want to first check the type N case for 5D. Suppose there's a Weyl double copy relation in 5D, we believe we should first recover that for type N case. Okay, that's the decomposition for the Weyl scalars. I mean, this is the only piece are left for type N solutions. Correspondingly, we will have only non-zero Maxwell scalars. Now it's a degenerate Maxwell fields, similar to the 4D case. There's some, well, I need to go back. Because of Weyl double copy relation, which is very transparent in the spinor language, it's simply the connection between the Weyl spinor and the Maxwell spinor. We hope or we believe this relation can also be valid in 5D. Somehow we are trying to verify these relations. So we also need the spinor formalism in 5D. While in 5D is very somehow, I mean, I would say kind of strange, because this is somehow we really, I mean, construct by hand. For the first 4 dimensions, we use the same Van Weyl matrix, but we also introduce the gamma 4 for the extra dimensions. Now the small, well, for each components for the capital A and B, you define a 2 times 2 matrix. So here, any components here basically is a poly matrix, all the ipsum, the Levi-Civita tensor. Okay. Well, that's for the spinor basis, you are no longer allowed to use the standard iota omicron, but you have to somehow massage them to build the spinor basis as a 1 times 2 matrix. So here is like for each components for this capital A, you will have a 2 times 2. Sorry, here is either you take a 0 or omega 2 here. Now we just package them. I mean, for the small a, the index small a, it's just either K1 or so here the small a, I mean the index small a, just package this K1 and K2 as my similar basis in 5D, and the same for the N. Well, whatever for the details, but now here I want to show you that for 5D type N spacetime, the only non-zero little group bispinner for the Weyl tensor is this guy. Now the point is the Weyl double copy relation is only about this Weyl spinner and the Maxwell spinner. So we believe somehow if you have a Weyl double copy relation in 5D for type N spacetime, those relations must be satisfied. Or somehow this is the 5D Weyl double copy relation generalized from 4D. And why this is like proportional, not exactly equal, because in 5D you have more components. You have to somehow introduce more scalar fields like this way. Here we propose we should use 2 complex scalar plus 1 real scalars to somehow realize a 5D Weyl double copy relation. Now here, those relations are nothing but a generalization of Weyl double copy proposals from 4D to 5D for type N spacetime. So that's everything I can show. Then the next step is, can we prove, or what can we verify from the equation of motion? Well, then this is a very somehow subtle question, because in 5D spinor language, we don't have the equation of motion. We don't know how the Bianchi identity or the Maxwell equation is written in spinor language. We only know that for the tetrad formalism. So then we have to go back to the tetrad formalism. So the point is we use spinor language to write a Weyl double copy relations, or the proposed Weyl double copy relations like this way. But we cannot prove anything from the spinor language. We transform or we convert the relations to the 5D Fieldline formalism. And the next step is like what have been done for 4D. We run for the Bianchi identity and apply the Maxwell equations to recover the equations for the scalar fields. Yeah, please. Yes, that's what we will show. That's what we want to show. We can just go back a bit to the 4D case. Like this equations is what we want to recover for 5D. And also we want to prove if they are integrable, etc. Like, yeah. 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 So we want to somehow recover exactly the same relations as 4D. Yeah. But we need to know what should be the relations in 5D, right? This we can only know from spinor language. So I think I can skip all the spinor stuff just to let you know that if you believe there's a Weyl double copy relation in 5D, then in the Fieldline formalism, this for type N case must be those relations. Next step, we will use the Bianchi identity of those Weyl scalars, also simplify from the Maxwell equations to recover the equations for all the i's. Yeah. Well, of course, we even for the simplest type N case, we find it's very hard to somehow to isolate the equations for all the i's. Then we propose the reductions. we turn off some components or some Weyl scalars, and all the psi for I we set to 0. We want reductions for the type in spacetime because the generic one is too complicated for us. We cannot say anything. And then turn off some guy, and also there will be corresponding conditions for the small phi, and plus some conditions for the scalar fields. Anyway, in the end, in the reduced case, we only have these two group of equations. It looks very like the 4D case, but they are one extra equations from the extra dimensions from 5D. Mm-hmm. Yes. Reductions. So the point is, okay, sorry, here. So those relations are the 5D Bianchi identity. Those are the 5D Maxwell equations. So in 4D, I mean, if we also checked our computation are consistent in 4D because we can also directly turn off some guy, turn off the extra dimensions. We can go back to 4D. In 4D, you have those two. You have those two. That's all. But in 5D, you have one more equations. Somehow you have one more degree of freedom. And then the 5D Weyl double correlation is simply this guy. And we somehow repeat the 4D case. We recover the equations for the scalar fields. Now it's a 5D relations. You have three equations. Corresponding with the integrable conditions, you need to verify there are three groups, not only one group. We prove that the integrability conditions are satisfied. That means for any solutions for the reduced 5D type N solution, there must be a Weyl double copy decomposition. Also, we prove that if your S satisfy this group of equations, S must be satisfy the source-free wave equations on the type N background. Literally, we can recover everything from 4D to 5D. For this, only we need a reduction for the 5D type N solutions. We need a reduction. Yeah. Also, we somehow checked this. This is also valid in 6D. Suppose you allow me to introduce 4D-like reductions. Then the next question is, how about type D case? Well, for the type D case, it's somehow subtle because the type D Weyl double copy relation is based on the known solutions, Plabansky, Damiansky, right? You suppose you know there's most general solutions, and then you start from these solutions. In 5D, we don't have that. In 5D, there's very few solutions. For instance, we know Myers-Berry solutions. What? Anything else? I don't know. Maybe a Golder solutions. Probably that's everything we know, right? Then we consider that probably first we should ask in 4D, can we recover the Weyl double copy relation from the equation of motion level? Namely, can we repeat the type N procedure for 4D type D case? That's our first question. Then we try that. And then in the end, somehow we succeed with some conditions. Let's say in 4D, now it's only about 4D type D case. For 4D type D case, well, suppose also you are in MP formalism. I assume somehow you know that. In the Bianchi identity, I mean, the only non-zero Weyl scalar is psi 2, and you have 4 equations from the Bianchi identity. You also have 4 equations for algebraic general Maxwell theory. Now, if you insist a Weyl double copy relation like this, you can repeat the type N procedure. You find the equations for the scalar fields like this way. Now you will have 6 equations for the integrability conditions, right? Because you have 4 differential equations. Those 4 are independent operators. Luckily, we proved that the integrability conditions are all satisfied. This is a very non-trivial check. Also beyond the previous proposals for type D. Now we recover this from the equation of motion level. We somehow can guarantee that for any type D solutions. Now you should really somehow specify that there's no uniqueness theorems telling you that Klein-Damiassi is the only type D solution. It's just we believe is the most general. Now we prove that for any type D 4D solutions, there must be a Weyl double copy relation. Yeah. And then the next step is which kind of equations for the, I mean, this is the first order differential equation. And we show that if the scalar fields satisfy those equations, it must satisfy like a Weyl-like equations, but you have somehow a source term psi 2. Well, somehow this is reasonable because for type D solutions, normally you have black holes. With this source term, somehow we believe this equation is even valid at the singularity because this psi 2 is somehow to compensate the singularity from the black holes. Okay, that's like a second realization of type D Weyl double copy relation in 4D. Then the next step we have done, I mean, in our second paper is to generalize the 4D analysis to 5D for type D case. Again, we need a reduction. It's not for generic type D solutions because I can just go back several pages. You can see for why this is very complicated for type D. Because for type N, you only have this one piece. For type D, you have all the 4 pieces. It's very complicated. Then we decide to turn off some of them just by hand. Turn off some of them by hand. We try or we test if in this reduced case we can recover a Weyl double copy relation, and we succeed. Well, the guys from the extra dimension should be 0. You see? Yes. So now it's not like a KK reduction. It's just we turn off the components associated to the extra dimension, but the extra dimension is still there. It's still there. Yeah. 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 And then, I mean, I think I have repeated the same procedure for 3 times. Here is everything that's go straightforward. We derive the equations for the scalar fields and prove the integrability conditions. Now we have 10. In 5D, we have 10 because you have 5 equations. The integrability conditions, there are 10. And luckily, we have proved all of them. In the end, we find the scalar equations, like the wave-like equations, like this way. You have a Weyl scalar plus this spin coefficient term. Well, in the beginning, we were curious because spinor coefficients somehow is gauge dependence because you can choose you can take a null rotation like a Lorentz transformation can change that. But in the end, we realize that why this direction is special because we choose the reduction. Somehow we set this extra dimension in a very special way. You can check the derivation tensors with this extra M4. You find this spin coefficients is only non-vanishing components. It's the expansion of this special 5th directions. So it's left in the scalar equations. Somehow it's telling you how this extra dimensions evolved in the 4-wave equations. So I think that's all the story I want to share. Okay, thank you.
Okay, any questions?
Yeah, yeah, yeah. Yeah.
I think this technology say something about very difficult questions in black holes in 6 dimensions. In 4, there is lots of no-go theorems. In 5, there are topological restrictions, so it's under control. In 6 and higher dimensions, it's very, very difficult to say even what is the black hole solution, what is the horizon we may expect, what is the topology of horizon in 6 and higher dimensions. Can we use this technology to say anything about possible black hole solutions?
Okay.
Classification.
I think, yeah, I think there's the answer is both yes and no. Well, the point, if you go back to the Weyl double copy relations, sorry, can I have yeah, okay. Well, in the beginning, when I tried to learn in particular Weyl double copy relations, for instance, for the type N case, I thought it's like converting conditions. Once you have solutions from Maxwell theory, there must be a solution of gravity theory. But then I realized this is not the case. The whole point of the classical double copy relation is you can only prove that for each gravity solutions, you can do the decomposition. You cannot do the inverse one. So in this case, you cannot say anything about gravity solutions. I mean, you cannot see how can we find new solutions from this construction? This is no, because but there are good things I will see afterwards. So so here everything we know is about a known solution. You give me a solution, I can prove this solution can have decomposition. But the positive hint is from our reductions. We really believe that in higher dimensions, those like the CMPB classification is still not good enough. You need to refine the classification. Like here, we introduce the reductions. Like we turn off all those guys. This is like a special case of this type N solutions. We find interesting properties. So somehow, can we use this reduction to somehow construct a new classification for solutions in higher dimension? I would say this is very possible.
Yeah, I think
asking about general gravity solutions, which is obviously very, very difficult. I'm just asking about black hole solutions. Let me ask more humble question. Let's say 4 dimensions, we have these noble theorems. Is there any translation for these noble theorems, or in 5-dimensional topological restriction, in the language of this double copy, the gauge theory language? Can we translate it to known fact about the gauge theory?
Like even is there anything special about
Yeah, exactly.
Yes.
Yeah. Okay. I think that's very good question of good directions, and that somehow is how can we use some techniques from gravity to learn about gauge theory? Is that somehow a summary of your question? Yeah, I think I would like to see progress in that direction. Also, I think that's very good question. But at this moment, we are working in formalism itself to higher dimension. But afterwards, I know that, but somehow, people are thinking the inverse direction because they want to understand like the singularities from these double copy relations. Because we know the singularity from gauge theory, we know a Coulomb solutions. This is like a delta function there, but we know nothing about Schwarzschild. What is the singularity? No.
For example, can you say anything about this censorship in the language of the theory?
Well, from my point of view, at least there's a hope because you can really somehow suppose you prove there kind of decomposition in this way, that's already something special. And then once you are while pose this question to the gauge theory, like which kind of conditions you should satisfy, I think this can be useful techniques.
Yeah, okay. I was just wondering maybe other questions. Okay. Regarding this, maybe along the lines of what Hussein was asking, when you do at this particular scheme reduction, like you say, you in a sense like avoid this MNPP classification, and then you consider like a particular reduction. Is there like have you tried to see the universal feature if you try to lift this to higher dimensions or any universality?
Well, not yet, because we at least
looked at 5D.
while we are focusing on the well double copy relations, not about solution or classification at the moment. So it's only somehow we just figure out this is an interesting reductions because somehow there's a reason.
You develop a certain prescription, like a scheme.
Yeah.
In terms of this boost weights, which you switch off and which you remain.
Yeah.
This probably along the lines if there is a properly chosen unique scheme can lead to a particular class of solutions like Ken was referring.
Yeah. But for us, we still somehow we need to learn. I mean, why this is interesting, but at least the Weyl double copy relation gave us some motivation to look at this kind of reductions and or refine the classifications, and we hope we can learn something from this, but not yet. We are not really good at finding solutions or geometries.
All right, I see.
Thank you.
All right. If there are no questions on Zoom, let's thank the speaker again.
Okay, thank you.